All right. Good afternoon, everyone. We're actually going to be starting the class right away. This is our final class, last and final class, and we're going to cover every other thing that we are yet to cover, and then we'll wrap it up. So I won't be waiting any longer for anyone. The recording will be made available, so because we actually have a lot to do today. So today, basically, we're going to be looking at dimensionality in scikit-learn or in machine learning, and then look at how we can build pipelines, right? So we look at feature selection and building pipelines, basically. That's what we have for today. But I'm going to have to look at creating the ROC curve that I've told us how I was going to do for days. So that's what we're going to start with before we move into the main thing for today. So I'm going to just quickly show us how we can compare different models using ROC AUC curve. Right, so remember I've already taught us how to evaluate our models using different metrics like our accuracy score and all of that. But there's a more there's another metric that I think I told us about, which is the AUC score basically. And what the AUC score tries to do is it tries to distinguish how well your model can. It tells you how well your model can distinguish between classes, basically. All right. So it is a more perfect or balanced score to use in evaluating your model. All right. So in simple terms, AUC is the probability that your model ranks a randomly chosen. This is a technical definition. It tells you how well your model ranks a randomly chosen positive example higher than a randomly chosen negative one. Don't get confused about that. It's just a technical term, and in simple terms, it's basically telling you how well your model that you've created can distinguish well between two classes. All right. So, and it does this by using different thresholds. Remember, I told us what threshold is, that your model gives a probability value as prediction, but then your threshold will not determine which class it falls under. So when you're computing your AUC score, it automatically looks at different thresholds, right? All possible thresholds, and make the classification. And from that, it will now generate what we call false positive ratio and true positive ratio. So these are the two values that would be used in computing your ROC curve and your AUC. So it's quite a lot to unpack, but let's just look at it quickly. So we're going to be using 3 different models, right? So we're going to use logistic regression, we're going to use decision tree, and we're going to use KNN, all right? So we're going to be using the load-based data set from scikit-learn data set. So I'm just going to import tree here. Import decision tree classifier. Then from scikit-learn neighbors, import KNN classifier. All right, and also from import scikit-learn data set, import load breast cancer. All right, so I'm just going to run this. So we are really not doing anything. I'm just showing you how we can plot the AUC curve. And actually, there's a function to do that. And the function is scikit-learn dot metrics. There are 2 ways of plotting your AUC curve, right? The first way is by using this function, which is called ROC curve display, right? So you import this from your metrics. This is what helps you display your ROC curve. Right? This is the easier way to do it. This is when you're just working with one model, right? You can just check it. But if you want to compare across different, we're going to use the other method I'm going to be showing us, right? So next thing we're going to be doing here is importing our data set. So we're going to load our data set. I'll come here and say data equals to load breast answer. All right. So we're not exploring the data or anything. We just want to go straight to building the model. So our X is going to be data dot data. Our Y is going to be what? Data dot target. And we're going to just split our data, So we need to import that. So from scikit-learn model selection, import train test split. All right. Am I correct with that? Model selection. Okay, yeah, that's great. We're going to, let me just delete this one here. Delete this. All right. So we're going to split X train Y X train S test Y train Y test. So it's going to be train test split function. So we're going to have our X and Y data. Then we're going to have our test size to be 20% and our random state to be 20. All right. So we split our data, which is fine. Everything is going well. So just go ahead to training our models. All right. So first we train logistic regression. So I'm just going to initialize it. So it's going to be log model. So I'm going very fast because I've gone through this thing already. So it's not new to us. I just want to get to the point where we can just compare the models. So we have logistic regression, right? I'm not putting any parameter here. You're just everything as default. So we have decision tree. We're going to call that tree. So it's going to be decision tree, no parameter. Just so we can be fast, we have key nearest neighbors classifier. So we initialize our model, then we're now going to use it to using the algorithms to train different models. All right, so just come here and say log model dot fit X train Y train. All right, so tree dot fit X train Y train. All right, I have KNN dot fit X train Y train. All right, so then this is, let me just train everything, right? And we're going to have everything ready, so we can now use it to evaluating our model basically. So evaluating our models using ROC curve. So this is where I want to get to actually. So now you've gotten a model. Let's say you finish all the training and you've gotten to a point where you need to evaluate your model. You check that accuracy and all of that, but you also want to use your AUC score, ROC AUC to evaluate your model and compare across different models. So that's basically what we're going to do now. So the first method is by using the ROC curve display. All right. So remember we imported it here, right? Or is it ROC curve display? So if you check it, you see that it does what? It basically just uses it's used to display your ROC curve. So this is the first method, right? And this is just where you want to just get the ROC curve and the AUC score for a single model. So to do that, you just paste it here and then you pass in two okay, actually there's a function that you're going to use from it, and it's going to be from predictions, right? From predictions, and then you're going to pass your Y, your true Y label and your predicted Y label. So you need to get your predicted while label by just coming here, and your predicted while label should be your probability predictions, not the class prediction. Remember, there's a difference between that. For probability prediction, we use .predict, model .predict. For class prediction, we use model.predict, right? Class. While for probability prediction, we use model.predict proper. Okay, so please don't forget this. So what we're going to be using is the probability prediction, not the class prediction. So this is for probability. All right. So we're going to just come here and get all our models. So we have log model dot predict prober. So we're going to have what? Our X test. Okay. So this is going to be log predict pred, right? So we're going to do the same thing for KNN. We have tree. So it's going to be tree. This is going to be tree pred. All right. So you're going to be tree dot predict prober, and we're going to have X test here. We're going to have for KNN as well. KNN pred equals to KNN dot predict prober. We're going to have S test. So you've gotten the probability value here, and then that's what you're going to use in making your prediction. So first thing I'm going to do here, I'm going to just do that, and then come in here to creating the RC curve. So using the first method, right? So I'm going to use the first method here. So take this away from here. Using the ROC curve, we're going to basically just come here and say ROC curve display dot from predictions, all right? And then you're going to put your true label, which is what? Y test. And then this one is going to be for what? This is going to be for logistic regression model. So we're going to put log pred. All right, so that's all you need for that. And once you do that, you're going to see what exactly is the issue now. Let's see. Okay, so I think there's a problem somewhere. Let me check my dimension. Log pred. Okay, so basically when you make your predictions, right, using prober, you're going to get a two-dimensional array. So what you're going to do basically is just to get either of them, either this one or this one, right? So you just come here and do something like this. One, so you're going to be getting slicing the second column basically, right? So this is how you do it. This is how you extract the prediction value when you're using predict prober. So if you're using your class probability, it shouldn't be a problem. So you can see now we already have it in one dimension. So sorry, I'm going very fast, but just we need to cover up. So that's it. Now it should give you your ROC curve. So you can see here that we have our ROC curve, and this is what it looks like. Right, you can see now the AUC score is also indicated here in the legend, right? The AUC score is 98. So this is a very good way to know if your model is very good or not. So this shows you that your model is doing very well actually. So you might be getting a smaller accuracy or a higher accuracy, but basically your AUC curve it's going to tell you, it give you a better insight on your model basically. So we can do the same thing for tree, right? You can do the same thing for tree. You see that tree is what? 94, right? Which is not as good as the logistic regression. You can also do the same thing for KNN. You can see KNN is 94 as well, so the same performance as the tree. So this is how to this is what I expect you to do. This is the main comparison I would be expecting, right? So AUC score. And this particular method is the first method, right? It's just simple, straightforward, and all of that. but I will expect you to use the second method, which I'll be showing us very briefly. So, which is we are going to be using matplotlib, right, for your ROC call, for ROC call. So this is the second method here. Second method. All right. So before we do that, I would like to ensure that we are using a particular plot style. So before I do that, I have to import from matplotlib import pyplot as plot. All right. So I want to use the ggplot style. So I'll say plot.style use ggplot. So anything that has to do with plot to affect it, basically, even this plot I just did now, right? Under the hood, scikit-learn is still using matplotlib. So if I change this, you're going to see that we have a new design, basically, right? So that is why I expect you to do in your project, use a clean theme, a clean plot style, and not just the default. So it's part of the whole project structure, organization, and everything, basically. So I want you to create something that you would actually be proud of. So this is how you can compare or get your ROC AUC curve manually. All right. Now let's look at using the ROC curve display function. And now see how we can do it manually using matplotlib. So I'm rushing with this because it's not the main topic for today, and we actually need to maximize time. So the second method is using matplotlib, basically. So in matplotlib, we are going to actually get the probability value of every single model. So we've done that already. And then the next thing we're going to do, we're going to get the FRP, false positive ratio, and true positive ratio, right, using what we call ROC curve. So we're going to import ROC curve here from our metrics. So we imported metrics here. So we just import metrics, ROC curve here, right? So this ROC curve is what we're going to use. And then we'll come here and we will just basically create each of them for each model. So for logistic regression, we're going to say FPR, false positive ratio, for log, for logistic regression, true positive ratio for logistic regression, and then thresholds. All right. And then we're going to say ROC curve, and we're going to put our prediction values, basically. So the prediction value we're going to put in here is our probability prediction. So we're going to put the main one, which is our S, this is the true label, and then we're going to put Y pred log. I think it should be log. Okay, log pred, right? So it's going to be log pred. So we'll do the same thing for KNN. So we're going to say, let me zoom in a bit too. Yeah, I've zoomed in here. So we're going to say FPR for tree, PPR for tree, and then the threshold. Okay. So we're going to have ROC curve, and then we're going to have Y test, and then tree pred. So we're going to have the same for KNN. So you can use any number of models you want to use. I'm just using that as an example. We're going to have KNN. So make sure that the labeling is descriptive enough, because you are working with 3 different models. Okay. So KNN, and then we have TPR for KNN, and then we have threshold. The reason why we are not giving threshold specific names, because we're not going to be using threshold values. The threshold is basically not going to be used. So let's see, unless there's a need to do that. But what we want to just get the AUC score, basically. So this will be Y test and KNN pred. Okay. So if you check this ROC curve description, you will see that what it does is that it computes the receiver operating characteristics, basically. So, and it outputs, what is the output here? So these are the output, basically. It output FPR, which it calculates all these things, basically. So it does this calculation using threshold value. So it's, your model gives an initial probability value, which will not be classified. So depending on the threshold you give it, it's now going to classify it as either this class or that class. So ROC call function does this classification for all possible thresholds and use the result to calculate the rates of false positive rates and true positive rates. So that's the value you're going to be getting as the output here. And the threshold here are basically the gradient threshold or the decision function used to compute the FPR and TPR, basically. So this is what you're going to be using to compute the FPR and TPR. So don't try to like scratch your head, right, about this. Just understand the process of this thing. So this is the first step. So we've done this now. Now the reason why we are getting the FPR and TPR is so we can compute the AUC score, right? So we need to compute the AUC score and also use it to compute our chart, basically. So I need to finish this up in 30 minutes so we can get straight to what we have today. So computing AUC scores. So now I'm going to come here and say AUC. So we imported AUC, ROC. So we have to import AUC as well. So come here and import AUC. This is going to help us compute our AUC score. So I'm going to just say AUC log equals to AUC FPR log and FPPR log. Okay, that's the first one. So we have to do the second one for tree. AUC tree is equals to AUC FPR 3 and TPR 3. So we did the last one for the last one. So depending on the number of order you have to like just do it for everything. So AUC FPR KNN and FPR TPR KNN. Okay, that's it for the AUC score. So you've computed the AUC score. So if you want to see the AUC, you can just come here and say AUC log. You see that AUC is not different. So I have to run this and then come back here and run this. You see that this AUC log is the same thing as we have here, where we did this particular first method. So you just have to approximate it to just 2 decimal points. So this one is what for this one is for KNN. So let's check KNN here. KNN. So you can see it's 94%. So the same thing here, 94%, right? So it's exactly the same thing, just different methods. So the reason why we're using second method is so we can compare across the different models in the same charts, right? So after we've computed the AUC, then we can now go ahead and compute and plot the ROC AUC curve. So this is where you're going to have to just describe something. So you use your knowledge of matplotlib to do that. So the first thing you're going to do is to create a plot. You can choose your figure size if you want, but I'm just going to go with the default. I'll say plot.plot. Since you are just plotting like just plotting your normal plot, you use plot function, right? So you come here and say you're going to plot FPR against the TPR. So here we have the true positive ratio against the false positive ratio. So the true TPR will come first, true PR log and FPR log. And then you also have your label basically, right? So that you can distinguish between them. So you're going to use string formatting so that you can like put dynamic variables there. So this one is going to be logistic. This is for your legend, logistic regression AUC score. All right, it's going to be something like this, and we're going to have this AUC log here, AUC log. All right, so simple as that is as simple as it is. So because we need to convert this to decimal point, you can just come here and say dot to f. I hope you've not forgotten this. This is simple matplotlib, right? So I'm just going to copy this and paste for the 2 other models. So we're going to change this to tree, change this to tree, change this to KNN changes to KNN, changes to decision tree, changes to KNN, come here, change it to tree. So don't make sure you don't make mistake in the variable naming, because it can be tricky. So after you've done that, you can now just do your X label. So X label equals, so your X label is this true positive ratio. So you can just come and say true positive ratio. All right. And then your Y label rather, and your X label is going to be your what? Positive ratio. All right, so that is basically it. So you have to show your legend, because you are plotting 3 different plots on one figure. So you have to show legend so as to know which one is which. So if you plot it without legend, this legend function, it will not show you your legend. So let me just show you what I mean by that. So if I do this, I'm going to get okay, this is upside down, so I have to like do it. There we go. Just do this. So FPL would come first here. So it's not upside down. All right, so this is basically what you're going to get. You see that we're having 3 different lines basically, compared to this one where we just have 1 line. The manual method can allow you to plot multiple models on a single chart, so you can compare them straight out, like by just looking at them. So in this case, we're going to let's see, just put your legend. So I just wanted to show you why you need to put your legend. The legend should be here, right? I'll run that, and you can see that we now have the description here. So this red line here is this one, which is our logistic regression. The blue line is our decision tree, KNN is our purple line. So you can see the difference scores 0.98, 0.95. You can see in this case, logistic regression is the one with the best performance. So this is how I expect you to make your comparisons, right? And you might build different models, or more than 3, let's say 4, 5. So you have everything here, comparing them together. So it's pretty straightforward. That is how you plot your ROC curve. All right. So this is just to make everything clean and good. So that's basically it. And there is also something I want to show us. Like once you've created your model, you can actually save your model as a file. So you can share that file with somebody, and that person can use that file to do whatever it is they want to do. So this is just a side note, saving your model, I think as Pickle. So you can either use joblib or use Pickle. So Pickle is inbuilt with Python, while joblib you have to install it. So using job, let's just use joblib, because I think joblib is easier and straightforward. So I'm using joblib. So you have to import joblib, right? So I'll just come here and say pip, the same way you installed XGBoost, install joblib. All right, if I install that, I can now import it, import joblib. So to do that, you basically just come here and say joblib.dump, and then your model name, right? So your model name in this, the model you want to like save can be either of this model that you have here. So you have your KNN, where is our model again? So we have our KNN here, log model tree and KNN. So any of them, you can save 3 of them. So let's save log. So we can save log model, and then we now like select the particular name you want to save it as. Let's say my logistic regression model. All right. But I always advise you, whenever you're doing anything about naming, just put underscore. Don't use white space. Logistic, my logistic regression model, and the file extension name is .pkl, right? That is how we store models basically. Pickle file, so .pkl. You then like close it and you run it. So automatically it saves it. So if you go to the directory where you save it, you should see something like that. So you can see where is that? Okay, let's go back. Be sure that 24. Anyways, you just go to the directory. I can't find the directory where I saved it, so that's why I'm basically not seeing it. So you go to the directory where you see where you are working, and the model name should be in that exact directory. All right. So this is 24. So where exactly is 24 here? So where is 24? 24 isn't here. Anyway, because of time, just find it where you saved where you're working in your current working directory, where that file, that notebook is saved, and you should see it there. All right. So yeah, I really don't know. So yeah, you can see we have other ones that I saved. You can see the ones that I saved here. Where is that? You can see it here. I saved this logistic regression.pq. This was like last cohort. And I saved this one as well, the decision tree model. So I can send it to you now, and then you can now use my model by unpacking it to like make predictions, right? So it's actually pretty straightforward. So that's how we use it. So you can see, you just check your job lab, you see how the main features and all of that, how you can do the whole thing and all of that. So yeah, that's it basically. So if you, let's say you have your model, you can come and say joblib.load, all right, joblib rather .load. So you now put the name of the model you want to load. Let's say my logistic regression model .pickle. Let's say someone sent it to you, you can just put it here and then wrap it in a string, right? And then you can see we have it here. So you can just assign it to a variable log model, right? And you can, if you come here, you can see you can just use log. Okay, let me just make it log model 2. All right. So log model 2 dot predict. If I come in and say x test, you can see that I can do exactly the same thing I can do. So you can save it as a file, the same way you can save CSV file, same way you can save any other file. So your model can be saved as a file and sent to wherever it is you want to send it. So this is how you can unpack it. This I've showed you how you can load it and how you can unpack it using joblib.doc to load it and save it, and using joblib.load to unpack it. Very simple, very straightforward. It's basically like not like complex at all. Yeah, thank you. Let's see. BYD. Anyways, that's just that's going to waste our time. So that's it. That's how we can like work with ROC AUC code. Pretty straightforward. So you can now implement it in your project, and yeah, like that is just it. So we have two options: using the ROC code display or using the manual method. So yeah, the recording will be made available for you to go over again in case you didn't get exactly everything I explained. Let's go over to today's class. So today we're going to look at building machine learning pipelines and also dimensionality reduction, right? So we're going to look at these two. Okay, someone said I should use PWD. I think that should work. PWD. Okay, it's in my root. It's in my root folder. Yeah. Thank you very much, Esther, for that. So, for those of us that want to like know exactly which directory we are currently working in, just use the pwd. I'm going to show you. So, I think if I go here, I'm going to see my file. So, just check it. Let me go. Okay. The thing is that I brought. Okay, should be it here. All right, so great. You can see it here. My logic regression model.pickle. That's great. It's just 1 kilobyte, like very, very small. So depending on the size of your model, you're going to see the corresponding size. And what this model is basically parameters and weights that have been stored inside it. So it's basically the knowledge of what it has learned that has been stored here. As simple as that. So yeah, that is it. Let's move on. All right. So today we're going to look at building machine learning pipelines and dimensionality reduction. So basically, we are going to look at two important things. First of all, we're going to look at dimensionality. And I'm happy that I've already explained what dimensionality is to us already before now. So I won't have to start going over it again. So remember what I said about dimensions. Dimensions are also features, right? So when we call or mention dimensions in ML, we're also talking about the features of our data set. So there's what we call the cost of dimensionality in machine learning, which basically refers to the problem that arises when working with high dimensional data sets. All right. So when working with high dimensional data sets, it can negatively impact the performance of a machine learning model, basically. So I think I've given one of the impact, which is overfitting. So and it has some other things, basically, you would have to use more compute, right? When you have higher dimension, your model might easily overfit, right? So these are the two basic problems that you might encounter when you have a high dimensional data set. But there are actually techniques that you can use to reduce the dimensions of your features, all right? So there are dimensions that you can use, techniques you can use to reduce the dimension of your features. So you can see this curve here, all right? So this curve is basically showing us the relationship between our model performance and the number of our features. So you can see here that as the number of our features increase, the performance of our model increase up to a certain point where no matter how much extra features we have, it would not increase the performance. Rather, it would even start to negatively impact the performance of our model, which you can see as we have on the screen, a downward slope, right, in this graph. So you can see now that this is the relationship between dimensionality and model performance. So sometimes we might need to actually reduce the dimensions of our data. And we're not necessarily just dropping features randomly. We actually want to retain all the information from all the features, but still yet reducing the dimension. So it's actually, okay, Justice, let me just explain that so you don't get confused. I don't necessarily mean more features, less performance. So now for traditional machine learning, there's actually a cutoff point where no matter how much extra data that you bring in, it will not impact the performance of your model. It won't change anything, right? It might even start to affect your model performance, right? Especially when it has to do with features, right? So the algorithms, these traditional algorithms are not so powerful enough to deal with these large complexities, right? So when you show them too much features, they try as much as they can to understand it, and up to a certain point, they begin to lose track of what they are understanding. So that's basically what happens. So the models are not powerful enough. The algorithms basically are not powerful enough. So it's a different case when you come to machine AI and deep learning. So it is the opposite is the case. In deep learning, the higher the number of dimensions or the features or the data or whatever, the more performance you will get out of your model. All right. So that's basically the difference between traditional, that's what we call them, traditional ML and deep learning. So deep learning works or thrives well when you have higher dimensions and a larger number of data sets. But when it comes to traditional ML, it can work well with a lot. And when I'm talking about number of features, right, I'm not talking about small number, 20, 50, 100. I'm talking about a lot of features, like 1,000 and above, right? So when you have a lot of features, it might start to negatively impact the performance of your data. So the more features you have, the better, but up to a certain point, right? For traditional ML, up to a certain point. So there are some of this, we encounter some of this, and we try to like apply some techniques to reduce the dimension. And one of the techniques is called PCA. So that we're going to look at this quickly. PCA, which is called Principal Component Analysis. I don't know how many of us have heard about PCA before, but this is a very important technique that is used to work or to reduce dimensions in machine learning. So before we get there, we can just we'll look at some key concepts, right? So we have explained what the cost of dimensionality is. So the cost of dimensionality occurs when adding more features make data analysis and model training harder. And this applies mainly to these traditional ML algorithms that we've listed, all right? So all the ones we've looked at so far, they mostly fall under this category. But when you get to advanced machine learning, like deep learning and the rest, this doesn't apply. It doesn't apply. So it just applies to what we are looking. So try to understand the difference and just separate them in your head, so you don't just generalize. Now we also have to look at what high dimensional spaces are. So with more dimensions, data point becomes sparse, making it difficult for models to see the same thing basically we're saying. So the implications of high dimensions is that you have to increase computational costs, right? So you have to increase the computing power that you use to like understand the patterns in the features, all right? Sparsity of data, which basically means data points spreading out, leading to overfitting, which I've explained. Distance metrics. So obviously, KNN doesn't do well with high dimensions, right? I think we said it when we were explaining KNN. So obviously, that one is already known. So model complexity. So basically, these are just the things I've explained so far, right? It's actually not something new to us. Okay, so I'm just going to breeze through it, and so we go to the main thing for today. So an example is like, a visual example is, in a 2D space, a circle can cover a lot of points. In a 10D space, a similar hypersphere covers much less of space. So this is not something that you can actually visualize because you don't know how 10 dimension is basically, right? But what we are trying to say is that two-dimensional space can actually capture a lot of information, right? Than if you want to capture more information, 2D will capture more information basically, right, in a bigger space. While 10 in a 10D space, it will cover more the same information or more, covering using lesser space basically, right? So this is just trying to like just explain exactly what this dimensionality is and how higher dimension can be costly basically. So the practical example here, this is we're just trying to just water the graph basically. The main thing here is just to understand that high dimensional data set, not just high dimensional data set, like the data set with a lot of features, like too much features. So especially when you're building your models, and you can't actually know until you build the model. So there are some models that would actually take more features than other models. Like for example, XGBoost will actually take a whole lot of features than logistic regression or than VM or than KNN basically. So you will not necessarily know until you build your model and you can see that your model is not performing well. So all these things would actually stem from poor model performance. So from there, you now start to investigate what exactly is happening and all of that. So now we have some strategies to mitigate this cost of dimensionality. We have PCA. So we have dimensionality reduction techniques, which we're going to look at. We have PCA, we have TSNE. So PCA is very, very, very like a very, very nice and important technique. We're going to look at it. And testing is also another one similar to PCA, but we're not going to look at CISNE. We're just going to look at PCA. So we also have like feature selection techniques, right? We have filter method, we have wrapper methods, and we have embedded methods. So these methods are what we use to also like help in mitigating dimensionality. We looked at some of this yesterday, but we're still going to look at them generally, all right? So we also have regularization techniques, which we looked at already. So we're not going to talk about this. So let's just move forward. So let's look at the first one, which is PCA under dimensionality reduction technique. So PCA basically is a dimensionality reduction technique used to reduce the number of variables in a data set while preserving the most important information. So this is what I need you to understand. It reduces the number of variables in a data set while preserving the most important information. So PCA doesn't drop variables. It doesn't drop features, all right? It applies a transformation technique that transform your features to what we call principal components. So those principal components is like a summary of your features. So if you have like 100 features and you want to use PCA to reduce the dimensions or to reduce the features to a lower dimension, so let's say 20 features. Now, what you're going to get as an output is not 20 features. What you're going to get is 20 principal components. So there's a transformation that is applied to those 100 features that kind of extract their the information they contain into the principal components that you have as the output. All right. So this might be tricky to understand at first, but I think it will make more sense when you see the implementation, right? So PCA is one of those techniques that we use when handling dimension, basically. So there are actually some like mathematical stuff that goes into it. Like there are a lot of like things that happens basically to enable this transformation. So the key concepts here, we have variance maximization, we have orthogonality, we have dimensionality reduction. So I'm not going to go into explaining exactly what all these things mean, but I just need you to get the main idea first. All right. So the implementation is very straightforward, very, very straightforward. You just set the number of principal components you want, and then it will do all the transformation for you. So if you have like 50 features, and remember we looked at lasso regression, which basically select features. So it's kind of how exactly does lasso regression select feature? Can someone just remind us quickly? How exactly does lasso regression select features? What does it do? What is that thing that it does that makes some features to be dropped? I'm waiting for responses. There's something that happens. Anyways, I know the recording is not. Thank you very much, Kingsley. Thank you very much, Kingsley. Thank you, James. So Kingsley actually captures exactly what I wanted. It drives the coefficient of the less important features to 0. That's what it does, right? So making that feature to be dropped. Basically, when you multiply that feature value with 0, is going to like basically eliminate it. So that is what lasso regression does. It just drops each feature, retaining other features. But PCA doesn't drop any feature. So when we are reducing the dimension of 100 feature data set to 20 feature data set, PCA is not necessarily dropping every other feature and retaining just 20 features. PCA is literally using the 100 features, compressing them. In a layman language, what PCA is trying to do is to try to summarize the whole thing. So when you have, let's say, a 20-page book that explains a particular concept, all right, and you were asked to summarize that book into 2 pages. What you're trying to do is that you will try as much as you can to retain all the information in that 20 page to be within the 2 pages. You're not dropping things randomly. You're just trying to compress it to a summarized form of it. And that's what PCA does basically. It takes the 100 features and compresses it to 20. So that 20 features that you're seeing is like a summary. It still contains the information that you had in your 100 features. But obviously, there'll be a little loss of information, but basically it has summarized it. When you summarize something, there are some details that will not be in the summary, obviously. But the most important thing that you need to know, or the most important information, are captured in that summary. And that is exactly what PCA does, all right? So that's the simple explanation of PCA. So I want you to just have this explanation at the back of your head so that I don't want to go into the technical stuff so you don't like get confused. Anyways, so maybe in advanced classes, maybe if you're going into research and everything, you can now look at the breakdown and the mathematical stuff behind PCA. So that's what PCA does, and we can see how it is implemented in scikit-learn. So we can basically, let me just demonstrate it, right? So we have our data set here. So we have our data set, which is what? So we have X basically. So let me just even make it like this. Let me make it. Okay, we have data and we have. So I want to convert this to a pandas data frame. How do I do it? Quickly. Yeah, James, thank you. PCA, putting on long sentences into a word. Yeah. As frame, thank you. So we use as frame. All right. So let's just quickly look at it. Now we come here and say X. So yeah, these are features, right? So we have what's the shape here? We have 30 features basically, all right? I want to apply PCA to it. We want PCA to decompose our features. So what the technical term it uses is decomposition. It decomposes it to some principal component. So we want PCA to decompose our feature to a certain number of components. So I'm going to come here and just say import PCA. So we import PCA from the composition module. So say from scikit-learn dot decomposition import PCA. All right, that's it. So we can come here and say using PCA to reduce the dimension of our data. All right. So come here and say PCA, and then let's just look at the documentation quickly. So it has a particular parameter called end component. So what does end component basically mean? That how many components or how many features or how many dimensions do you want to reduce your data sets to? All right, that is basically what it is. That is the most important parameter, right? So how many components do you want to reduce it to? All right. So first of all, let's just choose n component. Let's say we want to reduce it to just, let's say 20. All right. So we have 30 before we want to reduce it to 20. So now we're going to just create the object. So basically everything in scikit-learn, you have to create an object of that class. All right. So when I come here, what am I going to use to like, how do you think I will apply this PCA object to my data set? What method would I use in this case? I know I've not told, but I think it's based, I explained it when we're looking at data preprocessing. So what method am I going to use now to like apply this PCA transformation? Remember, this is a data preprocessing technique, just that we didn't look at it previously. This is part of the data preprocessing technique. So what method am I going to use here? Yeah, exactly. So we're going to use the fit transform, right? So the same thing that we've been looking at so far. So you can use fit to fit it. So let's just use fit transform together. and we're going to apply it to just our X variable. All right, we're applying it because we want to reduce just the features alone. So we apply it to just our X variable. And when we do that, we're going to get an output. So you can see here that we have we have 10 basically. So let me just say PCA output X. Let me just say X PCA. All right. So if I come here and I say X PCA dot shape, you can see it now. All right. What do you think we are seeing here? Let me just print it out. Print F the after applying PCA. All right. So I'll come here and say before applying PCA. So you can see the difference here now. We've reduced the dimension of our data from 30 to 20. Can you see how slick that is? Now let's say we want to reduce it to 10. We'll come here and say 10, and then we'll come here, do the same thing. And you see that it has been decomposed from 30 to 10. So we can now start working with this particular data in our machine learning, right? So this usually happens when you have a high dimension, and you can see that the high dimension, the dimensionality of your data set is affecting the model performance. All right, so you can now try using PCA in improving the whole performance by decomposing it to a lower dimension, so your model can actually learn better. All right, so that's basically straightforward. You can see how easy that is, how simple that is. All right, so we have what we call PCA explain variance ratio. So it basically shows us. So variance in PCA is information. So when you hear of variance, because in this case, let's just scroll up here. And the key concept of PCA, we have what we call variance maximization. So variance maximization is the information itself. Remember I told you that in compressing the features to a lower dimension, PCA is trying to maximize information, and that information is variance, basically. So PCA identifies the direction or principal component that maximize the variance of the data. So all these things, I just need you to be just storing at the back of your head. So PCA tries to decompose our features to a lower dimension by maximizing the information, and the information is variance. In the technical term, basically, is variance. All right. So that's why we have this particular stuff here, explain variance ratio. And what this does, let's just come here and check it out. PCA dot explain variance. So we have explain variance. So this explain variance basically is going to tell us, these are the different features. Basically, it's going to tell us the variance that each feature or each principal component is carrying or is explaining. So in this case, we have they all have their meanings basically, and I don't want to really go into that yet. Let's see, the explain variance ratio is the same thing. So I would actually give this to you as a task. I know you're busy with your project. That's the essence of project, so you read more. Just go and read up on what explain variance ratio is and what explain variance is in PCA. All right. So that's it for PCA, right? So PCA is a powerful technique for dimensionality reduction that is widely used in fields such as machine learning, image processing, and data visualization. It allows us to reduce the complexity of a high dimensional data set while retaining most of the important information. By understanding and implementing PCA, data scientists can effectively pre-process the data and improve the performance of their machine learning models. Right? Something I need you to know is that you should be careful when reducing your features, right? Or decomposing your features. Because you can always decompose doesn't mean you just come and say, let me just decompose it to 2 features. No, you're going to lose a lot of information. So it's just like telling someone to summarize a 20-page book in 2 sentences. How much information do you think can be compressed into those 2 sentences? That is exactly what we're having here. But let's say in this case, we are saying, we're reducing it to, let's say, 15 or let's say 10. So it's just like saying summarize a 20-page book to 2 pages. So actually, we can actually like cramp up a lot of information in those 2 pages, and that is basically what PCA does. So let's just move on to the next thing here. Let's see. So we're going to look at feature selection, and there's actually a problem right now. I really don't know why, but okay. Just give me a second. Okay, so I really don't know why. Well, unusually, okay, let me just move on for now. I'm just going to bring it over there. So feature selection in scikit-learn. So feature selection is also a method to handle dimensions, right? So all these things we are talking about is just to handle our dimensions. We looked at the first one here, which is dimensionality reduction techniques, right? We looked at PCA basically. So T-snare is another one, but this one is usually used for data visualization basically. All right, so we're going to skip that. So then we're going to look at feature selection. And for feature selection, we're going to look at 3 different methods, right? So these 3 different methods are what we're going to be using to select features. So it's also a way to reduce the dimension of our data, right? So you can choose either any of them that you want to use. So feature selection is a process of selecting a subset of relevant features. So this is different from PCA. PCA doesn't select features, all right? It compresses features. But feature selection techniques select features, right? By removing some features and retaining some features, basically. So it's the same thing. As you are removing features, you are basically reducing the dimension. So these are some of the reasons why we select features. It improves model performance. We've said it over and over again. It reduces complexity, speeds up training. So we have several types of feature selection method. We have the filter methods, we have the wrapper method, and we have the embedded method. All right, so I'm just going to take us through the embedded method. The embedded method is the lasso regularization. So I'm not going to look at this, right? So we've already explained it in yesterday's class. The embedded method is model dependent, all right? So when you use lasso regression, you are using any regularization basically that has lasso regularization in it. You are using the embedded method because you are automatically selecting features, right? Without you knowing, you are selecting features. So that is what the embedded method. So you can see the embedded method here is model dependent. So it is built into models, right? That's why it's called embedded method. So the remaining 2 methods here we have filter method and wrapper method. So for filter method, we have 2 techniques. We have variance threshold and we have select k-best. So I'm just going to show us how we can implement it in scikit-learn. So for variance threshold, basically you import it from feature selection module, all right? And let's see exactly how that is going to work. So you import features. So the implementation are usually the easiest part. So I'm going to import variance threshold. So scikit-learn feature selection, import variance threshold, and import select k-best. So these are the 2 techniques under filter method. So what does filter mean? Filter generally mean keeping some things out and retaining some things. So that's what these 2 techniques, that are what these 2 techniques does. They keep some features out while retaining some features. So let's see how we can use the filter methods. All right, so for select k, for variance threshold, so let me just I just comment say variance. Okay, I didn't run this. You know what? I'm going to send this this material, this particular notebook. to the materials class. All right, so it helps you like just follow along when I'm done actually. So you can see what the variance threshold does is a feature selector that removes all low variance features. And what did I tell you that variance mean when it comes to features? What did I tell you variance mean when it comes to features? Exactly. All right. Variance basically refers to information. So whenever you hear variance, you are referring to info. So you can put it this way: feature is a feature selector method or feature selector that removes all features with low information. So all the features you have, they are carrying a level of information that relating to the target variable, basically. All right. So they have an information that's relating to the target variable. So each feature has that kind of information. So it is called variance. So what variance threshold does, it removes those features with low variance. So you actually have to indicate the threshold that you'll be working with. So depending on the threshold you set, all features, what is going to happen is that all the features would have their variance computed, right? If you have 30 features and you're using variance threshold method, first what will happen is that all the features will have their variances computed, and then all the features with a particular variance below the threshold that you've set would be removed or would be filtered out. Okay, so this feature selection algorithm looks at the features, not the desired output. So the same way with PCA, they are still processing techniques basically, right? So that's basically it. So this is a threshold. Features with a training set variance lower than this threshold will be removed. The default is to keep all features with non-zero variance. All right. Removing features that have the same value. So this is just like, these things are really simple, to be honest with you, right? These things are really simple and straightforward. So once you have fundamental knowledge in ML, learning the advanced stuff, it would be a breeze, right? So that's why I usually take more time to get you to understand the fundamentals. So, and these concepts are very important. Terminologies in machine learning, they're very important. If you can understand 70% of them, you are good to go. So we're going to have the threshold parameter. So the threshold parameter by default is 0. And what this means, if I should use this particular threshold, what do you think would happen? What do you think will happen? I need responses. I usually have this kind of answer because you guys are data scientists and I need you to think like a scientist. What do you think will happen here? If I use variance threshold equals to 0. Exactly. So no feature would be dropped. Thank you, Abdulhamid. Retain all features. Gabriel, no info will be removed. Allow more. It will remove features. No, it won't remove. We're going to explain something basically. Kingsley, no feature will be dropped. Yeah, exactly. No feature will be dropped. But if you have a particular feature that has no variance, right? Variance is like deviation, basically. It's like differences in values. That's what variance is. So if you have a particular feature that is a single value, like all the values for, let's say, your 1,000 observations, they are the same thing. What do you think will be the variance of that particular feature? Let me repeat it again. If you have a feature that all the values in the data set, that particular feature, everything is the same number, what do you think will be the variance of that particular feature? Remember, variance is variation. So you should be asking yourself, is there any variation in the particular feature, is there any variation in that feature? The answer is what? No. Then the variance will be what? 0. There is no variation. There is no variance. So it will be 0. All right. So that's basically what variance is. So in this case, where we set our threshold to be 0, so we are saying we should keep all the features that have their variance to be greater than 0, basically. So the threshold in this case is 0. So every single feature that its variance is greater than 0 should be kept. So if you have a data set that has 2 features that have the same values all through, they will be removed when you use the default variance threshold because they are literally not adding any information. But if all your features have at least 1 variance, they will be retained. All right. So let's just continue. So if I run this is basically what I'm going to get. Let me just come back here and say output. Okay, I'm going to say output.shape. Let me just copy this one here. So all the things are still data preprocessing and feature engineering techniques, all right? If we're applying so can you see the difference on the screen here? You can see that all our features were retained after applying variance threshold because no feature had a variance of 0. But let's increase this threshold now. Let's make this threshold to be 20. Can you see the difference now? Can you see that our variance has reduced basically? Sorry, the features have reduced to 7, just 7, because all the features that had variance greater than 20 were retained, and those ones less than 20, less or equal to 20, were dropped, were filtered basically. So this is how to basically how to like filter out your features. So you filter out features based on the variance, based on the capacity to hold information. So if I make this to 10, you can see, so depending on what you do, on the value you put, you're going to have a variance. So that's basically for variance threshold. So we also have another one called select k best. Select k best. So I hope you are still following. I hope everyone is still following up onto this point. Although I have somewhat like a bad news, might not be able to complete this class. I'm going to give us more information on that in a few minutes. All right, so we have select k best. So select k best, what it does is that it selects top features based on a scoring function. All right, so it does it based on a scoring function. So we're going to import it and see exactly what it does. So some of you might be wondering how we can determine values here. So the possible values for variance is what? Can someone tell us the possible value for variance? Possible value for variance is between what? Is between 0 and what? Infinity. All right? It's between 0 and infinity. So it depends on what you're doing. So variance can take in any value between 0 and infinity. So, but it depends on the variable or the features that you have. Some features have low variance, features have very high variance and all of that. So you just try out different threshold, right? So you can try, let's say 0.3. You can see that we have 11 features retained. You can try 0.1. You can try 0.05. You can try 0.004 and all of that. So you can see that variance takes any value between 0 and infinity. So depending on the feature that you're working with, some features might have very little variance. So I believe this particular feature we're working with now has little variance. So that's why we are seeing a lot of changes with just 0.0000 something, right? And that's why we also need to scale our data using standard scaler and min-max scaler, so we can have a kind of standard variance basically, and we can know how to consistently apply values across our data set. So it's not like you have a particular feature that this value is having the variance between this value is so high and it's different from these other values and all that. So it just causes inconsistency. So these are the things that should be pushing you to understand exactly what's happening. I'm not going to, it's not even possible for me to like expound on everything in this particular program, right? So I'm just going to give you exactly what you need and just leave you to build up from there. So that's for variance threshold. So for select K is the same thing, but what it does is that it uses a scoring function, all right? Using select K best, it uses a scoring function. So for select K, you can see that it selects features according to the K highest scores. All right. If you scroll down, you can see we have score function. So score functions here. Let's see. So we have classic, we have chi-square, and we have mutual info regressor. So depending on the kind of data you have, you're going to select either of these scoring function. So for classification task, you use chi-square, all right? You use chi-square or you use f-classic. So you use either of these two. For regression tasks, you use f-regression or mutual info regressor, all right? So these are the different scoring functions that you use, basically. So for this particular one, we're going to be using chi-square. And you can see, so I encourage you to always read this documentation because it helps you a lot, right? It even helps me remember some things that I might have forgotten. So in this case, we're going to be using chi-square, and we actually have to import chi-square. So we import chi-square from the same feature selection module here. So I'm going to come here and we're going to say, where is the feature selection module? I'm going to import chi-square, all right? So if any of us has done statistics before, we should know what chi-square is. Chi-square is a non-parametric statistical test, right? So I'm going to come here and I'm going to just put my score function, all right? So I'll say score function equals to what? Chi-square. Then followed by another parameter, which is K. K here basically means how many features do I want to select? So in this case, I want to select 15 features, all right? So it's going to compute the chi-square value for all my features and select the best 15 features. That is exactly what it's going to do. So I'm going to come here and just say K best, all right? I'm going to come here and say K best dot fit transform. And I'm going to just say, and for this particular select best, unlike the previous one, it takes both the X and Y variable, right? It takes both the X and Y variable because it is computing the relationship between each feature and the target, right? So that is what chi-square does, or any of the other ones. It computes the particular scoring function between the feature. It computes the chi-square value between the feature and the target and give you a score. So it's not something that it does independent of the target variable. It computes it together with the label. All right. So you have to put your X train here, X and Y. All right. I've been using X and Y instead of X train and Y train. Anyways. Okay, I'm supposed to use it on X and Y actually. So I'm just going to do this and I'm going to get k output. So I'm going to come and do the same thing here before applying k best. After applying k best, you can see that this is exactly the same thing. So I think there is I think an additional one. How it does that? KIS score. Top features is select. Let's see. Okay, I've seen my mistake now, and nobody's even correcting me. So it should be k output. All right, k output. What was the issue? This is k output here, right? Then issued. All right, so you can see it retains the exact same feature that we specify here. All right, if we have 15 here, it's going to retain 15. If you have, these are just different ways to reduce dimension. So I think you've gotten to know about the PCA and the different feature selection method, right? You get to know about variance threshold, select k best. So we also have wrapper method. All right, so for wrapper method, we have what we call recursive feature elimination. And what this does is that it recursively removes features and build models to identify the best subset. So this works with your model, all right? So you so this basically works with your model, all right? Let's go ahead and see how that works. Am I moving too fast? Please let me get feedback from us. Am I moving too fast? And are we following up until this point? All right, so let's look at the next one. We have the wrapper, not wrapper. We have the what's the name again? Yeah, the wrapper method actually. Wrapper method. All right. So for wrapper method, we have what we call recursive feature elimination. Okay. Gabriel, you just get as the thing be. Don't worry, you'll get to understand it like as time goes on. So recursive feature elimination, it recursively removes and build models to identify the best subset. So let's say you're using logistic regression. All right, let's even just try import. Let's import the feature first. So report recursive feature elimination from feature, let's say RFE. So when you are using when you are doing feature selection, you don't use everything, or you just select the best one to use from all these things that I just showed you. All right. You either use PCA or you use feature selection techniques. All right. So let's move forward. So we've imported RFE. I didn't like run that. So I'll come here and just say RFE. So what does RFE mean? So RFE is a feature ranking with recursive feature elimination. So it given an external estimator. So we all know what an estimator is. What does an estimator mean? Based on what we've looked at previously, what does an estimator mean? Exactly. An estimator basically referred to a model, all right? So given an external estimator that assign weight to features, right? E.g., the coefficient of linear model. So you can see how understanding all the things we've been looking at so far helps you to grab concepts and understand things better. So if you don't understand what a weight is, if you don't know what a feature is, if you don't know what coefficients mean, and if you don't know what linear model is, you are not going to understand the sentence that we just said here. All right? Given an external estimator that assigns weights to features, e.g. the coefficient of a linear model, the goal of recursive feature elimination is to select features by recursively considering smaller and smaller set of features. First, the estimator is trained on the initial set of features, and the importance of each feature is obtained either through any specific attribute or callable. Then the least important features are pruned from the current set of features. This procedure is recursively repeated on the pruned set until the desired number of features to select is eventually reached. I'm going to explain this. This sounds like Japanese, right? It sounds like a foreign language. So what we're trying to do here in a layman language is that you have a model, right? And the point of the whole thing is you want to select features. So just keep that at the back of your mind. What you're trying to achieve is to select features. And you're not just selecting any feature, you're selecting the best features. And the different techniques we have been looking at so far uses different approaches to select the best features. For variance threshold, it uses variance. For select k-best method, it uses different scoring function like chi-square, right? F-class tip and the rest. For PCA, it kind of compresses the feature. It doesn't select. It's not a feature selection technique. It's a decomposition technique. It decomposes. Is a summarization technique, summarizing your features into what we call principal components. All right. So these things, they are achieving the same goal, which is what reducing. Let me not say it. Let me ask us to know if we understand it. All these things I've explained so far, from PCA down to this RFE, what are they trying to achieve? Or what are we trying to achieve with them? Because once you have the goal at the back of your mind, it will be easier for you to understand every other thing that we are explaining moving forward. So what do you think everything that we've been looking at so far, what are they trying to achieve? Thank you. Those are said reducing dimensionality or reducing features. You are correct, basically. So it's for dimension reduction to reduce the dimensionality of our data. So we can use PCA, which reduces the dimension by compressing the features. It doesn't select features. It doesn't remove features. I need you to understand that PCA doesn't remove features like that. The same way variance threshold remove features or lasso regression removes features. All right. So PCA compresses it by transforming our features to a lower number of features. If you forget anything, don't forget the example I gave, which basically is summarizing a book to a number of pages. That's what PCA does. All right. So we'll move from PCA to feature selection, where we now talked about several feature selection techniques. We talked about the first one, which was what? We looked at filtering, which have variance threshold and select k-best method techniques, right? That's the first method in feature selection. We looked at the second one, which is what? Wrapper method. And the third one is what? Embedded method. So I said I'm not going to explain embedded method because I explained it in yesterday's class, which has to do with lasso regression, lasso regularization. So any model or algorithm that is using lasso regularization is using the embedded technique in feature selection. I think this is a good rundown of what we've looked at so far, all right? So let's just push with what we have so far. So let me now come and explain RFE for you. So what RFE does, let me like include the parameters. So we have what we call estimator, estimator is what? The model. So we're going to come and just say estimator. So in this case, let's just use log reg. So we already have log reg already, so there's no need to initialize it again. Log model, all right? So we have what we call n-best, number of features to select, number of features to select, all right? So I'm just going to copy that and just like put it there. And then this is where you have to decide on how many features you want to select, all right? Let's say I want to select 10 features. I'm going to put 10. You now leave it to do its magic to select that 10 features. So the whole thing that will happen is going to be based on how recursive functional elimination works. So, and I'm going to explain that to you right now. So this is a class which I have to create an instance for it. So I just say RFE, right? I'm going to come and say RFE dot feed transform. And I'm going to put my X and Y, all right? X and Y. So now, what is happening here? Like, one thing I want to get from you is that I want you to understand how all these things work so far. Like, I believe everything I've explained so far, you understand. So I will show you exactly how it is done, but also show you how this the thing works under the hood. So in case you don't want to see all these warnings that you are seeing here, and this is something I want you to like also include in your project as well. I want you to remove warnings, all right? And I believe I've showed you how to ignore warnings, right? In Python, you have to just come here, import warnings, import warnings, and you can say warnings, filter warnings, and then you just write ignore. All right. So if you want to know what it does, just come here. Okay, I've not run it yet. So you can see that it's basically, these are the different things that it has here. Okay. So yeah, this is just to ignore warnings basically. So if I run this one here, you will not see that warning again. If I run this here, if I run this, you'll not see that warning again. All right. So that is basically what the warning does. It removes those warnings that you have. But sometimes you need to know what those warnings are all about. But when you are done with your project generally and you are sure that the warnings are not necessary, then you can add a ignore warning. So it's basically like after you are done with everything you're doing, all right? So now let's look at what happened here. So I'm going to say RFE outputs. So I'm going to do the same thing I've been doing so far. Come here, copy this before applying RFE. After applying RFE, this is RFE, right? So you can see now it has reduced the number of features from 30 to 10. So everything so far has been doing the same thing, all right? So the only one that you don't have control over the number of features to give you is variance threshold. You can't be that, okay, I want you to give me 10 features. You can't. You just specify the threshold value, and depending on how many features meet that criteria, it will give you those features. So it's only in this select best RFE that you can control how many features you want, basically, and in your PCA, right? So what happened here was that we have our estimator here, all right, and we have number of features to select. Okay. So what happens was a recursive function elimination process. Now, there's a way to understand concepts. If you look at the name itself, it should give you an idea into what the particular technique is doing. recursive function feature elimination, rather, should be feature elimination. Recursive feature elimination. All right. So what this recursive feature elimination does is that it eliminates features recursively, right? So first of all, it trains a model with all the features. That's why we have the estimator there with that particular model. It trains a model with all the 30 features. Are we following? All right. You can see it here that first, the estimator is trained on the initial set of features, and the importance of each feature is obtained. Okay? So it trains the model on all the features and the least important feature, because after you train a model, you are going to have, let's say, a coefficient or a weight added to each feature. All right? It tells you how important each feature is to the target variable. So after you train that 30 feature, the least important feature will be eliminated, basically. So after the elimination, you are now going to have how many features now? You're going to have 29 new features. So then the same process would happen again. That's what we call a recursive. Recursive is something that happens repeatedly until you reach a termination point. So 29 features will now be trained again with logistic regression, and the least important feature after the training will be eliminated. So the elimination will continue taking place until you have the set number of features that you've indicated, which is what, 10. So once it gets to 10, it will terminate the whole process, and then it's going to remain just 10 features, and those 10 features will be your best features, right? Because you are eliminating the least important features during every iteration. So after one iteration, you eliminate the list. After another one, so when you get to 10, you would have the best 10 features. That's basically what happens in recursive feature elimination. I think that's clear. I think that should be clear enough, all right? So that's basically what happens for this trapper method, and it's straightforward. You import it from what? Your feature selection module, right? So you can see we have variance threshold, select k-best, chi-square. So these are the things you can use basically, right? There are few data preprocessing techniques and all of that. So let's continue with what we have. So we have embedded method. We've looked at it already. Okay. Which is lasso and all of that. So basically, you can just go back to the last class, and the recording is not available, and I don't know why there's a delay. Okay, the recording is available now, so you would see that in. It's actually available now, right? So if you go to the materials and resources group, you should see it there. And also, there is a link I sent us on Twitter, right? I just saw it on Twitter, on X, and I thought to share it with you. It's telling you about accuracy score and all of that. So this is how you learn, basically. Like, it's not just in class that you learn from other sources as well, randomly scrolling through social media. And one hack I'm going to give you to become good at what you are doing is to surround yourself with the thing you want to be, basically. So if you want to be a data scientist, surround yourself with data scientists, both online and offline, right? At least if you do that for a given period of time, you would see that there's going to be something like a diffusion process, like quote unquote, a diffusion process, that you begin to get the knowledge and information from those things you've surrounded yourself with, and at a point you now become what you are seeing. That's actually very true. So if you come to my feed, right, like there was a time I was like learning. If you come to my social media feed, almost every single thing has to do with data science. Every single thing, data science, data. If you come, you find it very boring, all right? You find it very boring because everything is centered around. I was so focused on getting to master this particular thing. I was so focused on getting to get this skill and all of that. So that's how you get to learn something very, very quickly. So if you're on Twitter, it's a good place. Follow people that post these things repeatedly. If you're on LinkedIn, follow people that do those things. And another way to learn, aside following and surrounding yourself, another way to learn is by teaching. Okay, I'm digressing a little bit here, right? Because I just want to say today is the last class, so you should prepare your mind to stay a little bit longer. So because we're going to do a lot of talking. So another way to learn is by teaching, and I can see some of us doing it on LinkedIn, which is a very good thing. Trust me, it's actually a very good thing. The first time when I started teaching, I have not taught before, right? I was like, I know these things, but I've never taught them, and it was scary because now people will be depending on me to transfer knowledge to them. So I have to be good at what I am doing. I have to know what exactly I want to teach. So the whole process pushes you to learn that thing to ensure that you can effectively teach it. So the teaching process pushed me to learn what I was teaching better. So whenever you hear anything like the best way to learn is by teaching, it is a very true stuff. Trust me, it is very, very true. If you can teach something, that makes you understand it. So if you want to learn something, try to teach it to somebody. And when you try to teach it to somebody, those places that you find difficult explaining are the key places you need to focus on, right? Those are the key things you need to focus on. There's this kind of illusion that we have an understanding of a particular concept until you try to explain it to somebody. That's when you know that, oh, I actually don't really understand this thing. So that is a very good marker or identifier for your knowledge lapse, all right? So those are just a few things I just feel you need to know. Let's just move on. Now we've looked at the different methods to select features and reduce dimension and all of them. So in conclusion, feature selection is a crucial step in building efficient and effective machine learning model and all of that. scikit-learn provides several of these tools, including filter, wrapper, embedded methods. So at this point, you should know how to select features. All right, you should know how to select features. All right. So let's just move on. So now we're going to move to the second part of. I don't know those people who are the people asking for. Like, were you not in the same in the class last week? I said attendance has ended in week 12, basically. So there's no attendance for today's class, right? Try to focus on what we are doing, okay? Like, there are a lot of things to unpack in this class. So please, let's try to focus. There's no attendance for today, all right? Thank you very much. So we're going to be moving to the second part of this class, which is building pipelines in scikit-learn. All right, building pipelines in scikit-learn. So we've looked at dimensionality and all of that. Now we're going to look at pipeline. So pipeline is basically a more efficient way of just like gathering things together. All right. So in machine learning, a pipeline is a sequence of data preprocessing steps applied to a data. So this is a sequence of data preprocessing steps. So that's basically what pipeline is. So you're going to see how that is implemented in scikit-learn. So we have the particular class, which is pipeline. So it's a class that helps streamline the process, ensuring all steps are executed in correct order and simplifies the workflow from model training to evaluation. The reason why I left pipeline as the last thing is because you need to have understood every other thing. You need to have understood every other pre-processing step, every other thing so far for you to use pipeline. So pipeline is like a way to wrap up everything in an efficient and simple manner. All right. So let's just move on. So what are the concepts? Why do you use pipeline? To streamline workflow, to ensure consistency, to enhance reproducibility, to simplify code. All right. So these are the reasons you will use pipelines in your project. All right. Okay. So what are the pipeline components? We have transformers and we have estimators. let me just tell you something. Once we finish this pipeline, I'm very sure that a majority of us would change our project to using pipelines. All right. So pipeline is like a shift from the normal way we run our preprocessing. All right. So but let's just continue. So these are the components. So I need to focus on them. We have our transformers, right? So our transformers are those preprocessing techniques that we've mentioned, right? All the preprocessing techniques that we've mentioned are our transformers, and our estimators are the models that we are going to be using. So how do we create a pipeline? So for pipeline, you first import it, right? Import pipeline from pipeline, and then you follow the steps and all of that. So you import all the preprocessing techniques you want to use. So you create a pipeline class and then the steps as well. So for each step, you're going to put the particular preprocessing technique you want to use, all right? And then you put the final model that you want to use for that particular for the particular pipeline that you're using. Then you fit your pipeline, and then you can make prediction. So we're going to see how to do all of this, and yeah. So let's just this is the last stuff for today. So let's just implement it and see how that would go. So let's go back to this. So as I said, I'm going to try to make this particular like, let me see if I can edit the session 26. Dimensionality to reduction and building pipelines. All right, so all right. So first thing first, you have to import pipeline. So you import pipeline from pipeline. I think that is the easiest import that we can do from. So you can actually just do it like this. scikit-learn import. You can say other import. So from scikit-learn dot pipeline import pipeline. What am I typing? Pipeline. All right. So that's straightforward. So you can now use your pipeline. All right. So you come here and say, there's really not much theory behind pipeline. It's just demonstrating what it does. So let's see what pipeline is. So pipeline will it sequentially apply a list of transforms and a final estimator. So if you have several transformation or preprocessing and transformation, feature engineering, everything, they are the same thing basically. So if you want to apply some transformation to your data set, you can use pipeline instead of doing it one by one after the other. You can just use pipeline, right? So you can apply a list of transformation and a final estimator. So the intermediate steps of the pipeline must be transforms. That is, they must implement feed and transform method. So the final estimator needs to implement feed and all of that. So we're going to see how to implement this shortly. All right. I hope everyone is still following. Please let me know if you're still following at this point. And just give us a little break, like a few seconds or a minute break to just like breathe a little, and then we continue. I hope if there's any question at this point, you can just ask. Like if there's any question you have, you can ask before we continue. If there's any question, just ask quickly. I'm reading the chat, so if you have anything before I just want us to slow down a little bit before we kick off, right? So pipeline is the second half and the final aspect of this program, right? Yeah, I'm so sorry about that, Roma. I hope you get everything sorted out. You're actually quite a person for still sticking with the program, regardless, despite the challenges that you might be facing. And I really hope everything gets better at your end. All right. Can we get all the features that are retained after feature selection? Yes, of course. The outputs are the features that are retained. Like you would get it is usually as a NumPy array. So you would know the features that are retained and the ones that are not retained based on the values. Class reps, your head is blocked. We have to defreeze it so that it would not be blocked again. People, your head is blocked. What will you say of your colleagues? Make we do pipeline first before I go. No waiting, I go tell completion matrix and SG boost. Okay, Gabriel. So what if when we remove some features and our model is not working well, what should we do? Now, Justice, before you apply feature selection, you don't just apply feature selection blindly. You make sure that you've trained a model, and the model, you're seeing the performance of the model is not really good. And then you start to like diagnose or investigate why your model is not working well. So you now start checking all these things. Check if it's because of the number of features, like if it has too much features and the dimension is affecting the model learning well and all of that. So you don't just apply things because you want to apply it. It stems from why your model is not performing well. You go through the normal process of your machine learning building, and then you iterate. Building a machine learning model is an iterative process. Remember we said it in our first class, Introduction to Data Science. It's an iterative process, basically, or in our machine learning class. You build first, and then you iterate to improve your model. So it's not something you just do once and then you are done. No, you iterate. You apply some things and you remove some things and all of that. So that's why I call the scientist, right? You try to decipher what exactly is working and why it is not working, and then add something to make it work better and all of that. So it's not a straightforward stuff, all right? My own body just the hot ML and not be malaria ML. Nice play on words. So now ML they do you. Well, don't worry, you'll be fine. Is it advisable to tackle class imbalance with the pipeline? Pipeline is not actually a technique. It's just a way to capture all the steps into one long and like streamlined step. So it's not a technique itself. So you can't actually do anything to undo class imbalance. I can't, Juliet, I can't extend the summation. The summation was supposed to be this week. The summation was supposed to be today or yesterday, but I extended it by a week. Let me tell you something that most of us don't know. most of the other classes, they are done. Like they are actually done. They are done with their classes already for a while now. We are the ones still having classes at this point, right? So they're even probably done with their submission, right? Probably today or Monday, I don't know. So we are the only one that are still having our classes and even submission extended. So there is no extension again. Our graduation for this particular cohort is after this next week is upper week. So where do you want? We have to still grade the project, right? So how do you want us? We can't extend anything again. Okay, please just understand that. We just try to use this week that is coming, and we're not going to be having any class tomorrow. I have decided that we're not going to be having any class. Nothing at all. I just want us to focus on the project from tomorrow. Lock in till you are done. All right. So, using PCA, can you lose some feature? You lose some information, but you are not losing any feature particularly. Right? If you listen to what I said, it compresses or summarizes the features, not drop any feature. Okay, so can we apply the pipeline in our project without following some complex step? Yeah, you can apply. Like as far as you meet the criteria for grading, you can apply pipelines, right? So how do I interpret 3x3 confusion matrix? What do you mean by 3x3 confusion matrix? Confusion matrix is basically has to do with true negative, true positive, false positive, and false negative. Anyways, when you are working with more classes, I think it should be possible. Anyways, you interpreted this. I think one thing about this thing is that once you understand the basics, like you should just be able to extrapolate it to any other thing because there are a lot of things you can't capture. All right, a lot of things you can't capture. So once you have like let's say multi-class predictions now, you like 3 classes. Obviously, you're going to have a 3x3 confusion matrix, all right? So you would use the same understanding you have of 2x2 to explain that one as well, all right, and to like just understand it. So there's really nothing there. Data science is not easy, sir. Nothing is easy. Nothing is easy, all right? Nothing is. So just pick the hard stuff and do it. So all right. So let's just move on with Abdulhamid. Please, I think for the capstone project, the features definition would have gone a long way to know how they relate to the target variable. Yeah, I think I get what you're saying. If you mean dictionary, data dictionary, yeah. But I feel the name are quite they explain what the features are basically. So I know normally in a standard setting, you should always have a data dictionary, but I didn't get data dictionary for this. But the variable names are sufficient, all right, at this point. So I think the only one that was a little bit, I don't know, just do what you can do, okay? Let's continue with pipeline, all right? So we have pipelines in scikit-learn, right? And we've already initialized our pipeline. So it should be a normal object pipe, right? So this pipeline, what it does, it applies a sequential step, okay? So it has one parameter called steps, right? And these steps are the things that you're going to like pass into your pipeline to tell it how to process your data, basically. Okay, so you come here and you just put steps, and then the steps are usually in a list. All right, the steps are usually in a list. So you have something like this, and then the list would be a tuple. So in this steps list, there will be a tuple. So each tuple will be a preprocessing step, right? So each tuple will be, this one can be scaling your variables. This one might be applying whatever, PCA, or this one might be simple imputer. So might be, let's call this one to be simple imputer. And this one can be like, let's say one hot encoding. So it can be your one hot encoding, all right? One hot encoding. And like that. So you can also have like your PCA and your model and all of that. So in like a typical project, you probably not have one pipeline. All right, you might have like, let's say, typically you have 3 pipelines, especially where you have categorical variables and numerical variables, because you don't apply the same preprocessing steps for a categorical variable to a numerical variable. So you would most likely have 3 pipelines, basically, in total. So I'm going to use a data set that we already used before, which is going to be our retail transaction data. So I have to, let me see, I would have to move out. I'm just confirm something. I would have to move this, my particular where is that? This particular, where is the name again? Data. Okay. I have to move it to where I have my data set, right? Here. Yeah. Right. So yeah, great. So I'll just paste here. All right. So that is session 26. All right, so just run everything again from start. So I'll import our data, all right. So data is going to be, let me import pandas. Okay. According to Python, you should have import first. You should have import first before you have from, right? So it should be separated in this way. Import pandas, import numpy. All right, so I'm just going to come and say pd.read csv retail transaction.csv. All right, so I believe this is it. But let's do some, like, let me see if that has worked. So data.head. All right, so we have this data set, so I'm going to be like using it. I'll just drop, is this complete? 1, 2, 3. All right, I'll just drop transaction dates and customer ID. All right, because we'll not be using it for anything. So I'm going to say df dot data is equals to, data, use df, okay. Df dot drop, and I'm going to say my columns, transaction date, which is this, and I have my customer ID, and then my axis equals to 1, and place equals to 2. So yeah, so I what's df, right? So this is basically it. So now let's assume this data set I'm working with. All right. Why is price not here? Okay, there's price here. Let's assume this is data set I am working with. I want to show you how we can use pipelines. All right. Although this data will not make sense for a machine learning project, but I just want to show you. So we're going to show you how to like preprocess our data using pipelines. Now, because we have two different data types, we have to like separate them, right? We have to separate them. So we'll preprocess them differently, because if you pass this entire data set in a pipeline, you're going to have an error, because some of the preprocessing technique doesn't apply to categorical variables, and some does not apply to numerical variables. So you have to separate them so you can preprocess them differently and then join them back together and then continue. All right, so that is basically the step you have here. So come here and say separating the data sets. So remember we did it before. Separate them into like categorical and numerical variables. All right. So I'm going to just I need my y variable, because I'm actually going to build a machine learning model. So let me just make y x and come here and make x is equals to df.drop is going to be my discount applied and then axis equals to 1. That's going to be my y-x, and my y is going to be df the discount applied, right? So I just assume these are target variable here. I think I just put them here. All right. So what I'm going to be working now is x. I'm going to be working with x. Delete this thing. Okay, so I need to separate the data set now. I'm separating them by categorical variables and numerical variables. So I'm going to come here and say cat variable, categorical variable equals to. So what formula or what method will I use to select only the categorical variables? All right. Great. So we're going to be using select D types. All right. To be we're going to have X, which is our data set. Select D types, and then we're going to exclude numbers. All right. So I'm going to come and say exclude numbers. All right. So now there's a little twist we're going to have here. We're going to just come here and select the columns and then convert it to a list. Let me even bring this up so I will show you what exactly I'm doing. So I have it for the numerical variables. We have the select the types and also exclude, include, numbers, and then columns, and then the list. All right. What's the issue? Numbers not understood. Let me see. It is there. All right, great. So if you print this out, you're going to see what we have here. You see, we just have the list basically, right? So at the end of everything, we're just trying to extract the names of the categorical variables and the names of the numerical variables. You see why we are doing this as we move forward, right? But this is the first thing you would do when you want to use pipeline. So the next thing is now like defining your pipeline. All right. So you're going to have numerous pipelines, not just one. So you're going to first have categorical pipeline. So a pipeline for categorical variables, right? So the first thing you're going to have is you're going to obviously be dealing with missing values. So you're going to have in this tuple, you're going to have your the pipeline, the particular preprocessing name. So you can put anything. You can just put imputer, all right, followed by what the particular class name, simple imputer, and then you can put strategy equals to what most frequent. Since it's a categorical, you want to use mode. So after that, you also want to like perform one hot encoder on your categorical variable. So you can just name this encoder. So this particular text here you have here, you can name it anything you want. Like the name should just be the description of the preprocessing technique you are using here. All right. So I'll just come here and say one hot and encoder. All right. So like you leave start output equals to true because you don't want to mess up your memory. So this is for categorical step. This is a very simple pipeline. Like depending on you, you might be having a whole lot of other steps here. If you have another step, you can just put your comma and then come here and put your third preprocessing step, and so on and so forth. All right. So depending on how many preprocessing that you want to do, you would have them all lined out here. So this is for categorical pipeline. Then you have to do for numerical variables. So come and say numerical pipe equals to pipeline, and then you do the same thing. Steps equals to this, and then in your list you're going to have the tuple of the steps. So the first step in this case, I would my imputer, all right, and it's going to be simple imputer followed by what strategy equals to. So we are going to use mean, okay. Then the next thing is going to be scaling. I want to scale my numerical variables, all right. So come and say standard scalar, then that's it, all right, scaling. So that's basically That's basically for our categorical and numerical pipelines. All right. So now there is something that you would need to do. Since you already like separated it, you need to combine them again. All right. You actually need to combine them. And there's a particular class that we use in combining two pipes. It's called column transformer. Right. So we are introducing another new thing to us now, which is called column transformer. So I'm going to come here and import. Can we use min mask killer? Yes, of course. Like, this is just an example, basically. Like, you can use every other thing I've taught you, you just use it as you wish or as you think it's necessary. That's why I keep saying that this is not a, like, I'm not giving you something that you should follow. I'm just giving you a pattern that you can, like, learn from and then implement based on what problem you're working on. Right? I'm not expecting to follow exactly everything I'm doing. I'm just explaining things to you so you can like use it in your own as well. So you can use whatever scalar you want here. It's not necessarily like standard scalar. Okay. So you import your compose, your column transformer. So it is in the, you can see that we are introducing a lot of module now. We import that from compose module. So import column transformer. Run that, and then we're going to come here and so then we'll now combine the two pipelines. Combine the two pipes. All right. So for the column transformer, we are basically just going to combine the categorical pipe and the numerical pipe. So we'll come here and say column, I will say combined pipe. Let's say combined pipe. Combined, let us use combined equals to column transformer. Then let's check what column transformer does. Why is it not working? So column transformer it applies transformation to columns of arrays or whatever. So let me just show you how it works basically. So that so you have your numerical variables, your numerical pipes and your categorical pipes. So you just come here and put in a bracket which will take in a tuple of steps or a tuple of your two different columns. So the first tuple is going to be for your numerical, and the second tuple will be for your categorical. Or first tuple will be for your categorical, anyone in any order. There is really no order to this. So what I'm going to have inside the tuple, I'm going to have the string describing this particular column. This is a categorical column, all right? And then it's followed by what? It's followed by my categorical pipe. And then you can see now that we actually got our categorical variables here. So we'll now bring it back here and say apply this pipelines process to these variables, all right? So then we'll do the same thing for numerical process. I'll say numerical column. Then I'm going to come here and just say numerical pipe, and then num vars. So these are combining these two. So we're not going to run it now, basically. Like, we are just going to define everything. So after that, you now define your final pipeline. Define your final pipeline. So at this point, you've preprocessed all your data and you've combined them into one data. And then you can now decide on what to do. So let's say I want to apply PCA to my data because the process of encoding would increase your features. So let's just assume you want to reduce the your features, right? Or decompose the dimension. So I can just say, let me apply PCA. I'll say final pipe. So you can decide what to do in your final pipe. my spelling on the numerical pipe. Don't worry, when I get an error, I will know. So final pipe is equal to pipeline, and then so you have your steps. So let's just say the first step is going to be my PCA, applying PCA, right? So let's come and say PCA and n components equals to, let's say, 15. Okay, sorry, I don't have, let's just say 10. Okay, and then the next thing that follows would be, like, after I've done all of this, I would now want to, okay, before you apply your PCA, you actually have to, like, bring in this combined pipe that you have here, right? So you bring in that combined pipe. So you bring in it and you just name it preprocessing. So this is the preprocessing. Am I writing? Preprocessing step, and then you put the combined pipe there. So just put in combined, right? Then you have, after you apply this transformation to this point, then the data set that you've combined, you will now apply PCA to it, right? You're using the features to just 10 principal components. After that, you can now perform build your model. So the next step is now model building, which we are going to be using log model for it. So we have our logistic regression model, right? So this is basically going to be the steps for our pipeline. So now if you run this, nothing is going to happen, basically. Line 15, what happened? Line 13. Let's see. If anybody can see the error here, just let me just parenthesis error. I just want to be sure that I'm not missing anything here. Okay, this one is for this. All right, this is for this. This is for this. This right here is for this. This right here is for this. Okay, yeah, this is it, yeah. All right. Simple imputer. Okay, I have to import simple imputer and the other one. So I'll just come and say from scikit-learn dot impute import simple imputer. Also from scikit-learn dot processing import non-hot encoder and standard scaler. All right, so I think those are things I need to import. Is there another thing? Okay, pipelines. Okay, I think this is the correction that Jacobo was trying to get me. So pipelines. All right, thank you for that. Which one again? Steps. Okay, steps should have equal to. Why is that? Step should have. Okay, no wonder this thing was not making sense to me the other time. All right. Okay, great. So we've defined our pipeline. So this is all the preprocessing that we want to apply to our data set. So after we've defined everything, the next thing now is to apply the pipeline to our data set. All right. So after we've defined, so the definition process is the most important process of our pipeline. So we have to ensure that we define our pipelines and we ensure that it is well defined and it is what we want to do. So we'll now come and say pipeline or final pipe dot fit, and then we're going to pass in our data x train and y train, and then we're going to run it, and we're going to have an error because what's happening here? Y contain NEM. So we didn't okay. So let's preprocess everything before we separate it. So let's just do that. So let's just make this data df rather df all right, so I'm going to come and do this. So it processes every single thing. So you can just come here and then separate it. All right. So the same way we separated it here. The given column is not a column of the data frame. Which column is that? Discount applied. All right, so let's see. That is discount applied. Final part XY. All right. So just follow me as I'm debugging this thing. Column is not column of the data frame. So and we have Y. If anybody sees the issue, just let me know. All right. And all right. Still doing all the solution. The column is in the column of the data frame. Control. Okay, let's see. Let's do this first. All right, that's a numerical variable. Numerical variable, and we have numerical variables, pipelines, criteria variables, variables. So you see why you need to be extra careful with this pipeline, because you can land in issues like this. So although it's quite straightforward, but you just need to ensure that it is actually just probably a very minor bug, and this is the annoying kind of bug you have, like something that is just as a result of one omission. Let's see, number, and then you have a pipeline for cards, our pipeline for have a numerical variables here. Okay. First off, we actually missed it from the beginning, because we're not supposed to use linear regression for this particular process, right? Because the logistic regression, because the output is is a numerical output. That's our discount applied. All right, is a numerical output. So that's even where we got it wrong at the first place. We're not supposed to use logistic regression model for it. We're supposed to use a linear regression model, right? So I just use it that to just illustrate how we can use pipeline. So I'm just going to have to linear model. Okay, I import logistic model again. But I don't really think that's the main issue, right? But let's start from there first. So I'm going to define our linear model here. I'm going to define linear model. First linear expression for class. Oh no, I'm going to define it straight up in the Alright. So I think this is what I should have just done. I've just filled NA. Yeah. Just done this NA. So I'll delete this. Just fix the NA stuff here directly. Just say y dot QNA. I'm going to say y dot mean, and just in place equals to true. All right. So this same, where exactly is this thing coming from? Drop data set, discount applied. All right, let me see my data set again. I'm going to remove this from this and put this here. All right, so we have okay. Now I see the problem. I'm dropping discount applied here already, and I'm now trying to get it from here. So it should be X here, right? It should be X here and not DF. It should be X there and not DF. If I'm correct, this should work. It should be X there and not DF. So you can see how, like, it's at the end, it's just one simple stuff. So we're supposed to, since we've already like separated it here, we should be using X here, not the DF itself, right? Because for the DF, for the X, we already dropped it. So it is going to cause conflict here. So let's just move forward that. Now you can see our pipeline is showing us the different steps we took. So this is the preprocessing, the column transformer preprocessing. So this was everything that it did, then went on to like apply transformation on these particular columns, right? Simple imputer, one hot encoder on your categorical column, and then simple imputer and standard scalar on your numerical columns. Okay, so after that, then you combined the two columns and then applied PCA to it to reduce it to 10, and then applied build your linear regression model. So you can go ahead and just use it, final pipe, to make your prediction. So predict, and we just say X. All right. So that's it for pipeline. Like, it kind of does, it's put everything in a kind of streamlined step. So the main thing is defining the pipeline itself, right? So defining the kind of preprocessing you want to apply to it and everything that you want to do. So it makes your work even neater. It's not compulsory you use it, all right? It's not compulsory. It's just something that makes your work look a little bit better and even efficient, kind of. But it's just an option, another option, like to doing your project. So that's just it, basically. I'm going to share this note with you so you can look at it more. And then you're happy is not compulsory. So, and the video recording, I'll try to make it available this night because I believe we all need it as soon as possible. All right. So that's it, basically. It's let me see if we are done, basically. All right. Or is week 16. So that's it for pipelines, right? So pipeline can be actually very simple as just putting a single pipelines, and as more advanced or complex as creating multiple pipelines, depending on the kind of data you want to preprocess, right? Creating them differently, combining them, and then creating a final pipeline and having everything work for you. So data science is interesting, actually. I think I'll just use that word instead. It's quite interesting, and you'll enjoy it once you give it time. Once you give it time and like patience, you'll get to enjoy it later on. So you can use your pipeline to now do every other thing that you do, and just like get your model working. But it's not compulsory, as I've said. You don't need to use it. It's just another approach. But I would advise you to just try to learn it. Like it's something that is adopted quite common. It's commonly adopted. So I would advise you to learn it. So that's it for today's class. We're actually officially done with the classes for the entire program. So we've come to the end of our class. Yeah, this is the longest class we've had, almost 3 hours. That is 2 hours, 40 minutes, and still reading. So I think you need a clap at this point. Every one of you need to be clapped for, because it's not easy. It's not easy at all. It's not easy at all. All right. So no, Justice, you don't use train split. After you've created your pipeline, you can now like split your data set and then apply the fit to it, right? So you can see here that after you apply the pipeline, you can now come here and split your data set, say X train, S this and all of that, and then split and then apply it here, S train, Y train. So that's just because how it is, all right? So it's not easy. Like it's really not easy going for 3 months back to back to learn data science. Like even if you feel you've really not like achieved much yourself, the consistency is a pointer to something about you. Like it's not everyone that can do this, trust me. I just look at the number of persons on this live class now. We have just 53 participants. And starting from the beginning of this, we had almost 200, I think about 200 live participants. Like between, we get 200 at a point. We got 200 at a point. And so you can see how like it's not an easy thing. So you should be proud of yourself. You should actually just go out there and get yourself something just to congratulate yourself. Yes, it's a win actually. I know we are not done. We've actually not wrapped up like completely, but the fact that you can stay to the end of the class, to the end of the last class from beginning to end, is an achievement, is something. So keep it up. Like, I'm really proud of everyone here currently. You're doing well, and I would want to encourage you that it's not expected. It's not expected that you get to know every single thing that we've looked at so far, right? It's not expected, but the fact that you have stayed would you definitely have a base knowledge, a ground knowledge, a fertile ground for to develop the the knowledge to a better degree, right? So I would just want to urge you to go back to everything we've done so far. Try to pick up those things that you feel you have gaps in. Look at them, study on your own. And I think everyone should have a note, right? We actually underestimate the power of having notes. I have a lot of notes. Like while I was learning, I'm still learning actually, but while I was like intensively learning, I have notes that I can always go back to even at this point, right? To pick up some things. I can filled up notes from like the learning I did going back. So you should have note as well, like, on things that you picked up and all of that, so that you can go back to times when you learn some particular things and you probably want to remember it and all of that. So I'm actually just lost for words at this point. I just want to tell you congratulations once again for making it up till this point. I really would miss having these classes. I don't know if you enjoy the classes as I do, because I really do enjoy it. I really do enjoy teaching you. I really do enjoy like explaining stuff to you. I really do enjoy seeing you learn new stuff that you didn't know before, and getting to see progress, getting to see you grow, getting to see you like in real time, literally transform from a novice to someone that is comfortable with Python and can even like do some machine learning stuff, some basic machine learning stuff and all of that. So if you can comfortably do your project, like if you can finish your project, trust me, like you've gotten everything that you need to get. Okay? It's not expected that you get 100%. Like, and let me even be true with you. I forget some things sometimes. Right? Sometimes I have to look up some stuff to be sure that it's the correct thing. You can even see in some classes I forget some function some function names and all of that. So you're expected to know everything. Even there's some classes that I would have before some classes, I would just have to look up some things to be sure that okay, yeah, this and that, I'm still up to date before I have that class. So we are not like a computer that can store stuff and retrieve it immediately. We need what we call exposure to what we are learning frequently to be able to like actively retrieve it. So I'm not expecting you to be perfect. I'm not expecting you to be 100% like capable at this point, right? Because we've dished out a lot already, and I think you need a little bit time to just decouple them and understand them and internalize them and just make sense of the whole thing. Okay, so what I just need is for you to have a holistic idea. So you are not longer a novice. You're no longer someone that is new to data science. When someone is talking about any data science stuff, you can actually contribute. You can actually say something. You can actually just say one or two about it. Okay. Even when maybe you're having discussions regarding some of these concepts, you probably have an idea. Okay. Even if it's just one particular thing that you remember from class that I said, that even if it's an analogy or an example, you can even use it to explain it. So these things are like pointers to the fact that yes, you've grown, you've learned, you've developed skills, you've developed knowledge that are actually going to help you. So I'm going to encourage you to keep moving, right? Keep like doing what you're doing, to keep putting in the time, to keep putting in the effort, to keep showing up, basically, right? It doesn't end here. And I won't be there with you for the rest of your journey, right? It's not going to be feasible, basically, unless you decide to be part of the other class, the other program that I'll be having, the advanced program, which I'm going to be putting out very soon. Unless you're going to be part of it, then this is going to be our divergent points, all right? And I'm going to be wishing you Godspeed and wishing you the best, basically. I would love to see you in 2 years from now, 1 year from now, 6 months from now, doing something good. Like, okay, this person is actually like, have grown, has developed themselves to a higher degree. And these are the things that gave me joy, that the investment and the time we spent was not a waste. Okay? Trust me, this data science, learning data science is not cheap. Like, I don't know how else to tell you. It is not cheap. The financial aspect of it is not a small thing. So you should appreciate the value you're getting from this and hold it very tight. Hold it very tight. It's a lot of value, I'm telling you. So for those of us that want to continue with data science, please, I'm encouraging you to keep it up. Just give it time. Time is a revealer of a lot of things, and with time comes success. So you might not be where you are today, but definitely you are not where you were yesterday. But in 2 years from now, in 6 months from now, 1 year from now, you definitely be closer to where you want to be with consistency and time, and also patience, right? I can see so many of us saying that this class is elusive, we're not getting it, and all of that. It's quite normal. For something that is technical as this, it's normal. Like, trust me, it is very normal for you to have that reaction, all right? So the thing that you just have to do is, okay, we've learned this thing now. What did I understand generally about this class? All right. What was I able to get from this class generally? At least you should be able to capture that idea. Even if you don't understand the whole technical story, you'll be able to capture that idea. Okay, now this was the idea we got from this class. We understood how to work on dimension problem and feature selection and all of that. And we also look at pipelines. So these are the core ideas that we learned. Now, how do we approach all these things? Like, what are the implementation steps? So those are the places, or those are the scenarios or the places where you might start having some little issue understanding. So you are not expected to go back to it and figure out how to do those things. Okay. So just don't worry yourself so much. Like, it's you're going to be very good at this thing. Like, just trust me, you'll be good at it. I have my assistant tutor. I don't know if he's on the class right now, but he was part of the first cohort, and now there's even a program that we did, TIP, Talent Integration Program, where we actually grouped people into different groups to build a product. And they are doing very well at this point, and even about to, I think, launch a product, right? And it started from somewhere. It started from not knowing anything about data science to getting to know some things and getting to implement those things. And all these things happen because of the commitment that you put into it, the time, the patience, the belief in yourself. That's another thing. Like, you have to believe in yourself that you can do this. Like, you can actually understand all these things. It is just time. Don't start by telling yourself that I can't understand these things. But tell yourself that you can understand it. It's just time. I just need to put more time into it. Okay. Once you put more time into it and you break through, then you go up from there. And the more you understand something, the easier it is for you to understand more things, right? The more you understand what we have been doing and the more you understand concept, the easier it is for you to understand even more complex stuff. So it will be easier in the long run. Like now, if I want to learn maybe some advanced tools, remember AI is always developing, rapidly developing. So there are new concepts basically. So if I want to like read up some new tools and new architectures and all of that, it won't take me time. Like to be honest, because I've gotten to learn how to learn. So it won't take me time because I've learned, I understood all the fundamental concepts. So I just have to just read it through and I'll connect one and two together and I'll just map everything in my head and that is it. And this came as a result of consistent learning and persistency in understanding this base and fundamental concept. So I think I'm just going. I don't want to overstretch, but I'm just going to leave it at that. I'm proud of everyone here currently. You all are like real MVPs for sticking up to this point. You deserve like whatever it is that you want. Okay, so but just try to finish it up. Like finish up your project because we are still going to have project presentations. And as I said earlier on, that we won't be able to take in every single person's project. So we're going to be taking only those persons that I think top 10 or top 20 persons, right, to present their project. So please try as much as you can to put much effort into your project because this project is going to reflect exactly how to reflect how much you've learned from this program, basically, right? So, but even after the program, you can still actually continue with your project if you feel you didn't do as much as you should. Right? So you shouldn't just stop there. Even after the program, you can continue with your project because it's something that you can actually put out there that you're able to do this particular project and you're able to do this and these are the things you did and that and all of that. So yeah, it's something. It's a start for you. It's an addition to your portfolio and an addition to your CV. So yeah, that's going to be it. Your project is going to be ending on the 20th, and I expect us to all submit before then. And I will announce the date. We are going to be using 2 days basically. Anybody can join, but those that will be presenting are those that will be selected and are going to like let us know before time. All right. So thank you very much for your time so far for the past 3 months, for the past 12 weeks or 13 weeks. I've actually enjoyed this course. I have gotten to I've gotten to like I've gotten comfortable basically with you. Like it's been like we've known each other for like a long while and all of that. So it would be kind of off not having classes again every week because it's something I always look forward to. And seeing some names on the live class, seeing some persons commenting, especially Justice, always like typing and sending messages. Yeah, it will definitely be missed, right? And this group will still be available actually. We won't be closing the group. It will be there in case you need to like see anything or there's an opportunity or you just need to reach out to somebody. Yeah, the group will still be available for communication going forward. All right. So thank you very much for everything, for showing up. And you're asking, am I married? No, I'm not married. So let's just wrap up with the project and call it a day. So we also be having our graduation, I think, on the 28th of this month. So we also prepare for that as well. We'll be announcing the first the top 3 students per class or per field. Like that, each of the fields is going to be like data science, project management, product management, project design, front end, back end, cybersecurity. Everybody is going to be present there. We're going to give talk about your story and how the whole program went for you and all of that. So, anyways, we are going to get more details about that. So I'll just like give room for any other comments that would be made. So at this point, I'm going to be ending the recording. All right. So this is going to be your last official recorded class for this course, and yeah, we'll be drawing the curtain close at this point.